आज हम सॉलिड स्टेट फिजिक्स 1 का चैप्टर नंबर 2 स्टार्ट करने लगे हैं। क्रिस्टल बाइंडिंग एंड इलास्टिक कांस्टेंट, क्लासिफिकेशन ऑफ सॉलिड्स। Ionic crystal of crystal consisting of a lattice of ions held together by electrostatic interactions. They exhibit strong absorptions of infrared radiation and have places along which they cleave easily. An ionic crystal consists of ions bound together by electrostatic attraction. The arrangement of ions in a regular geometric structure is called a crystal lattice. Examples of such crystals are the alkali halides, which include potassium fluoride, potassium chloride, potassium bromide, potassium iodide, and sodium fluoride. Other combination of sodium, cesium, rubidium, or lithium ions with fluoride, bromide, chloride, or iodide ions. These solids tend to be quite hard and have high melting points, reflecting the strong forces between oppositely charged ions. The exact arrangement of ions in a lattice varies according to the size of ions in the crystal. A case study of NaCl. The properties of NaCl reflect the strong interaction that exists between the ions. It is a good conductor of electricity when molten melted state, but very poor in the solid state. When melted, the mobile ions carry charge through the liquid. NaCl crystals are characterized by strong absorption of infrared radiation and have planes along which they cleave easily. Structurally, each ion in sodium chloride is surrounded by 6 neighboring ions of opposite charge. The resulting crystal lattice of a type known simple cubic, meaning that the lattice points are equally spaced in all 3 dimensions and all cell angles are 90 degree. ये हमारे पास अब डायग्राम बनी हुई है, द स्कीमेटिक पिक्चर ऑफ NaCl क्रिस्टल स्ट्रक्चर्स। जो हमारे पास बिल्कुल फील्ड डॉट है वो हमारे पास Na है, Na प्लस है यानी सोडियम, और जो हमारे पास बबल टाइप में बना हुआ है वो है हमारे पास क्लोरीन। Na पर है यानी सोडियम पर पॉजिटिव चार्ज है और क्लोरीन पर हमारे पास नेगेटिव चार्ज है। How can one sodium ion surrounded by 6 chloride ions or vice versa be consistent with the simplest formula NaCl? The answer is that each of those 6 chloride ions sits at the center of its own octahedron, whose vertices are defined by 6 neighboring sodium ions. This might seem to correspond to Na6 chlorine 6, but note that the central sodium ion shown in the fig 2.1 can claim only a 1/6 share of each of its chloride ion. Reflects the ratio 1.1 stoichiometry of the compound. As in all ionic structures, there are no distinguishable molecular units that correspond to the NaCl simplest formula. Sodium chloride, like virtually all salts, is a more energetically favored configuration of sodium and chlorine than the elements individually. Next है हमारे पास covalent crystal. A covalent bond is a chemical bond that involves the sharing of pairs of electrons between atoms. This sharing results in a stable balance of attractive and repulsive forces between those atoms. Covalent solids are a class of extended lattice compounds in which each atom is covalently bound to its nearest neighbors. This means that the entire crystal is in effect one gained molecules. The extraordinarily strong binding forces that join all adjacent atoms accounts for the extreme hardness of these solids. They cannot be broken or abraded without breaking a large number of covalent chemical bonds. Similarly, a covalent solid cannot melt in the usual sense, since the entire crystal is one gained molecule when heated to very high temperatures. These solids usually decompose into their elements. Another property of covalent network solid is poor electrical conductivity. Since there are no delocalized electrons when molten, unlike ionic compound, the substance is still unstable to conduct electricity. Since the macromolecule consists of uncharged atoms rather than ions. This is also contrary in most forms of metallic bonds. A case study: allotropes of carbon. Graphite is an allotrope of carbon. In these allotropes, each atom of carbon forms three covalent bonds, leaving one electron in each outer orbital delocalized, creating multiple free electrons within each plane of carbon. This grants graphite electrical conductivity. Its melting point is high due to the large amount of energy required to rearrange the covalent bonds. It is also quite hard because of the strong covalent bonding throughout the lattice. However, because of the planar bonding arrangements between the carbon atoms, the layer in graphite can be easily displaced, so the substance is malleable. This explains the use of graphite in pencils where the layers of carbon are shaded. On paper pencil, lead is typically a mixture of graphite and clay and was invented for this use in 1795. Graphite is generally insoluble in any solvent due to the difficulty of solvating a very large molecules. Diamond and graphite, two allotropes of carbon. These two allotropes of carbon are covalent network solids which differs in the bonding geometry of the carbon atoms. In diamond, the bonding occurs in the tetrahedral geometry, while in graphite, the carbons bond with each other in the trigonal planar arrangement. This difference accounts for the drastically different appearance and properties of these two forms of carbon. Diamond is also an allotrope of carbon. Diamond is the hardest material known, defining the upper end of the 1 to 10 scale known as Mohs hardness scale. Diamond cannot be melted above 1700 degrees centigrade. It is converted to graphite, the more stable form of carbon. The diamond unit cell is face-centered cubic and contains 8 carbon atoms. ये हमारे पास द स्कीमेटिक पिक्चर विच शो द टू एलोट्रॉप्स ऑफ कार्बन. ये पिक्चर हमारे पास कार्बन के टू एलोट्रॉप्स को शो करती है. मज़ीद वीडियो के लिए हमारे चैनल को सब्सक्राइब करें ताकि हमारी आने वाली हर वीडियो आपको मिल सके. थैंक यू.